Hello, welcome back. This is Jonathan Gardner. We're covering Schroeder's An Introduction to Thermal Physics, and this is section 3.1, the first section of chapter 3, obviously. In this section, we're going to talk about temperature, what temperature is, and we're going to provide a definition of temperature that does not rely on thermometers and is very mathematical. And it's very much connected to the previous topic that we covered in chapter 2, which was entropy. Let's just really quickly review what entropy is. Entropy is the observation that because of probability, multiplicity tends to increase over time, right? So the second law says multiplicity increases. Now, entropy is related to multiplicity by Boltzmann's constant. This is the definition of entropy, times the log of the multiplicity, right? So we can calculate the entropy, and because multiplicity increases over time, then entropy is going to increase as well. It's basically, systems are going to find their maximum multiplicity. Now, he goes through in this section, he goes through and talks about how we can relate temperature to entropy and things like that. But before we do that, I wanted to go over the second part of this chapter, which I think is quite good. It's called a silly analogy. And so the silly analogy works like this. So suppose we have a world made of very strange people. And these people, what they're doing is they are sharing money with each other such that they can maximize the happiness. Okay? Now, the people, they're not focused on their own happiness, although that's important, obviously, but they're focused on the total happiness. So they're very, altruistic, I guess is the right word for this. However, some people are happier with more money than other people. Or if you give the same amount of money to different people, it'll generate different amounts of happiness. Okay? And typically these people, the way they work is their happiness curve looks like this. So as you give them more money, their happiness will go up. Okay? But there's kind of a diminishing returns, right? So if they don't have much money at all, a little bit of money will generate a lot of happiness. But if they already have a lot of money, then it won't generate so much happiness so quickly, right? Now, we might call this property, this tendency of a person that's willing to receive money, or rather their willingness to share their money with others who might benefit from it more. We're going to call this their, I don't know the right word for this, we're going to use generosity. That's what he uses in the book. Okay? So people that have a lot of money, that realize they're not getting that much happiness from their money, they're more than willing to share that money with people who don't have much money and who would generate more happiness from it, right? Because again, we're trying to maximize the happiness of the people. Okay? Now this analogy directly corresponds. Money is energy. Okay? The people are obviously systems or objects. And their happiness is the entropy. We're trying to maximize entropy. And their generosity turns out to be their temperature. Okay? So high temperature objects have a lot of energy in them that isn't producing very much entropy. And if they were to share some of that energy with low temperature objects, they would generate more total entropy. Now there's two ways to look at this from a kind of a philosophical perspective. One way is that you imagine the universe is conspiring against us, right? There's some magical creature at the controls that is looking at how energy is allocated and always pushing it towards the higher multiplicities, right? And I don't know that there isn't a creature doing this, because, this is beyond fundamentals. It's way beyond physics. This is like, philosophical reasoning type stuff. This is like Maxwell's demon type thinking. But to me, this is a very good way to think of it, that there is some magical force that is pushing things into higher entropy states, right? The reality is that this is a property of randomness itself, right? It's not that there's something pushing you towards a more likely state. It's just that that state is more likely, right? If you keep rolling the dice, you're going to get closer and closer to the average or to the most likely outcome, okay? Now, I did draw for you one graph of what people can be like in this analogous world. There are some other graphs you might see. One is like this, right? Where as the money increases, they get happier and happier, faster and faster. This is what he calls a miserly system, which does exist in reality. Orbits, planets, black holes have properties like this where you can just keep adding energy and the entropy keeps increasing, and so all the energy is going to tend towards those systems. Another kind of system that you might see in practice looks like this. So it actually, as you add energy, the entropy decreases. These are systems that tend to have a capacity, like a paramagnet. Eventually, if you keep adding energy to a paramagnet, eventually all of the magnets are going to be pointed against the field, and you can't add any more energy. In fact, by removing energy, you're going to be increasing the entropy. Okay, so let's get into the math now. This analogy is very useful. We're going to try to keep it in mind. Okay, so let's take two Einstein solids. So we have solid A and solid B, okay? And let's say this one has 300 for their N, which it's their oscillators, right? And the second one has 200. There's a total energy, okay? And we're gonna measure the energy in packets. And there's also a Q total. And we're going to share that energy such that we can find the maximum entropy. So let's draw a little graph of what that might look like. So we have QA increasing to the right, and since the total is always going to be the same, QB increases to the left. And we're going to see for QA it's going to gradually rise and then start to flatten out. And then for QB it's going to gradually rise and then flatten out in the opposite direction. Okay? And then there's a sum that kind of looks like that, okay? And this is the total, the Q total, this is QA, and this is QB, okay? And the maximum entropy is going to occur somewhere around here in this area, right? So let's look at the two slopes. Let's see if I think I got this pretty close here. This is pretty accurate. This is actually where we have 60 units of the 100 in A, and 40 in the B. So Q total is 100 because we're sharing 100 between these. Okay. And when we're calculating the maximum entropy, what we're looking for is we're looking for the place where the partial derivative of the entropy over the change in how we allocate the energy has to be equal to 0, right? So the first derivative, it's going to be flat where that's at its maximum. Okay, and we could take the second derivative to determine whether it's curving up or curving down. In this case, I think it's fairly obvious, right? And in our case, the energy packets are actually related. There's a factor that they're proportional to the internal energy of the system. So I'm just going to call that, instead of QA, I'm going to call that UA, the internal energy of A. Okay, and so we want to find where that is equal to 0. And this is the total. This is not the entropy of A. This is the total entropy. We're going to find where that's equal to 0. Well, if the total is equal to 0, then that means the sums of the entropy have to equal 0 as well. Okay. Note that we're doing this for the energy in A, so this is technically, we should change this to minus and the energy in B, because B is pointing the opposite direction. Okay, and so we end up with this really awesome relationship that the entropy in A compared to its energy has to equal the entropy of B compared to its internal energy, right? And so this relationship here, if we go back to our first chapter of the first section of this book, temperature is that thing which is the same when they come into thermal equilibrium. And in this case, we say thermal equilibrium is met when the multiplicity has reached its maximum state. And so the thing that is the same for these two objects is the derivative of their entropy with respect to their energy is the same. Okay? Let's kind of think about what this means. So let's go over here to this part over here. So we have a slightly upward slope, we have a slightly downward slope, and we have a steep upward slope. Okay? So over here, what's happening is the energy in A, if we were to add a little bit more, we would get a lot more entropy. But the cost of doing that would we would be decreasing the entropy in B by a little bit. So adding a little energy to A would give us a lot of entropy, but it would only cost us a little bit of entropy. And so the total entropy would increase over here. And if we were to go over to someplace over here on the right, we would see kind of the same little behavior, right? So if we were to add a little energy to A, we would get a little bit more entropy, but we would lose a lot of entropy from B, okay? And so we'd lose total entropy here as well, right? So over here, the total entropy says, hey, you should be moving to the right. You should be moving towards this maximum. Over here, it says moving to the left, right? And so these systems, you can kind of think of it as inside these little systems, they look at how much energy they have. They look at how much entropy they have, and they say, what happens if I get a little more entropy, or get a little more energy, or get a little less energy? What's going to happen to my entropy? And then they basically tell the other object, and they say, hey, you, if I had a little more energy, I could make a lot more, or a little bit more entropy. And that other object has to think about its own situation. Well, if I gave up a little energy, if I took on a little more energy, how much entropy would I gain or lose? And it's going to keep working its way out until it reaches this maximum point where the two slopes actually cancel each other out. Okay? That is the thing that is equivalent when we've reached thermal equilibrium. When these two slopes cancel each other out, we've reached thermal equilibrium. Okay? Now, that thing is temperature. Okay, but temperature is a little bit more complicated than that, right? Remember, temperature is their generosity, their willingness to give up some energy. And these are clearly their willingness, they're basically what would happen if we took on more energy. So let's continue some more math and see where we go. So we know that the partial derivative of the entropy of a system, when the two systems are in thermal equilibrium, that these two derivatives are going to be the same, these partial derivatives. And we're going to note that these are actually, we're keeping the number of particles and the volume constant, right? So we're not changing those, we're just changing the amount of energy in each system. Okay? And we know that there's something between these two values that are equivalent, right? Now in the book, he does a little bit of dimensional analysis, and he says, well, obviously this is 1 over the temperature, right? So 1 over the temperature is equal to the entropy, partial derivative of the entropy with respect to energy, right? And another way you can write that is you can say T is just, ds by du to the minus 1, okay? And we typically don't talk about du per ds because, like, thinking about the equation, how does the internal energy change when we change the entropy is a little bit backwards, right? Typically the entropy is defined in terms of the entropy. And so it's easier to calculate this than the inverse, right? So, but I'm going to go backwards, okay? What I'm going to remind you is that we're talking about this generosity. That's the temperature, right? So when it's high, that means they want to share. And when it's low, that means they want to, I guess, keep or get more, okay? All right, but in this case, this says that when it's high, that means we want more energy, and when it's low, we want less energy, okay? So, or we don't want energy as much. So if we were to take the inverse of this, then that would flip it around, right? Because ds by du, when it's high, it means it wants more, and when it's low, it doesn't want as much. Okay, so if we take this to the minus 1, then we will get the behavior we want. When it's high, it wants less, and when it's low, it wants more. Okay, so that's the reason why we say temperature. Now, we could have defined temperature as an inverse. We could have said temperature is measured, it's the inverse of what you're used to, right? So instead of being 100 degrees Celsius is boiling water, we could have said, oh, at 0.1 degree, we're boiling water. And at some other temperature, we're freezing water. At some greater temperature, it's absolute 0. There's some maximum temperature. We could have done it that way, but we didn't do it that way, right? We decided temperature increases as things get hotter rather than increasing as things get lower, right? So we're going to use from here on out, the definition of temperature is defined to be the partial derivative of S with respect to U, the inverse of that, keeping N and V constant. This is the definition of temperature we're going to use from now on. Okay, and just remember the analogy and what this means. A high temperature object says, hey, I have a lot of energy, but it's not really creating a lot of entropy. Does somebody else want to use that? And a low temperature object is saying, like, I don't have a lot of energy. I could create a lot more entropy. Please give me more energy, right? And that's what high and low temperatures mean. And that's what happens when you take a hot object and a cold object and bring it together, is the hot object starts sharing its energy with a low temperature object. Not because there's necessarily universal force, although you can think of it that way, but because the multiplicity increases, because it's more likely the energy will get allocated that way rather than staying where it is. So with this, we can actually calculate the temperature of an Einstein solid, okay? So we get a temperature of 360 Kelvin when QA is equal to 13 or 11. This is for the A system. So A has a temperature of A is 360 Kelvin, okay? And I forget what we calculate for the low temperature side, but we'll see that the temperature of B is less than that, okay, when QB is equal to 89 or 87. So you can go ahead and calculate that. He doesn't do it in the book. Okay, problem 3.1 is to actually calculate the temperatures of the various energy distributions. Problem 3.2 is to prove the 0th law of thermodynamics, which says basically there's this thing called temperature. More precisely, it says if these two bodies are in thermal equilibrium, then, and one of the bodies is in thermal equilibrium with the third object, then they have the same temperature, right? So basically, if A and B have thermal equilibrium, and B and C have thermal equilibrium, then A and C have thermal equilibrium. That's the 0th law. It's so obvious, especially in this context, why this is so, but it's important. In problem 3.3, this is part of the silly analogy. In problem 3.3, you're going to graphically solve the thermal equilibrium for two graphs. One has like a graph like this, and the other has a graph like this. And what I recommend is taking one of the graphs and flipping it, and then just adding them together or something like that. So you can see where the maximum is, and you'll see how the slopes and everything match up. Problem 3.4. If we were to take a miserly system, remember the miserly system is a system like this, where the entropy just keeps getting higher and higher the more and more energy we add. What would it mean to be in a state of thermal equilibrium with another system, right? So where would you find the maximum entropy if you were to add this with some normal object, okay? At this point, we can look at two real-world examples of entropy. So we can take our Einstein solids. Remember, the entropy of an Einstein solid is equal to Nk times the log of Q over N plus 1, okay? And so the temperature of this is going to be the inverse of the partial derivative of this with respect to U. Well, where does U come in? Well, U comes in because Q is actually related to the energy. So I'll just do log of U over epsilon. And epsilon is the size of an energy unit, okay? And so T, we can rewrite this as Nk log of U plus N, or minus Nk log of epsilon N plus Nk, right? So we can break out the logarithm that way. And when we take the partial derivative of this with respect to energy, so we're going to take the partial derivative of entropy with respect to energy in the minus 1. So that's going to be Nk over U to the minus 1. And so we're going to get T is equal to U over Nk. Okay? Or we can rewrite this as U is equal to Nkt, which you recognize from chapter 1. This is the energy of a thing with 2 degrees of freedom. So F is equal to 2 in this case, okay? Because we had 1/2 FKT is the energy of a system with F degrees of freedom. Okay. What about an ideal gas? Well, this is a little bit more complicated. S is equal to Nk times log of V over N times 4 pi mu over 3 NH cubed. Oh, I put squared, I think, on my website. I'm pretty sure it's cubed. Doesn't matter. It'll drop off anyway. Plus 5 halves. And so we can rewrite this as Nk log of V over N plus 3 halves Nk log of 4 pi m over 3 NH cubed. And then we can have 3 halves nk times the log of u. I'm just pulling the u out as another factor. And then we have 5 halves nk. And so when we take the temperature of that, that's going to be the derivative of this. So that's going to be 3 halves nk over u. 3 halves nk over u to the minus 1. So that's just going to give us T is equal to 2/3 u over nk. So we can calculate u for the ideal gas is going to be 3 halves nkt, which is what you expect, okay, for an ideal gas. In fact, you can even use this equation to go backwards and calculate the ideal gas only given the entropy of an ideal gas. Okay. Problem 3.5, find the temperature of a low temperature Einstein solid. So you have to go back to when we had Q is much less than N. Remember, this only works when Q is much greater than N. You have more energy packets than the oscillators by a large factor, like 100 or 1,000 or something like that. So go back and do that. It tells you what you should get, so you know where you should be going. 3.6, find the temperature of anything that follows the equal partition theorem, and then comment on what happens at low temperatures. So, you know, you're going to get U equals F over 2 nkt. What happens at low temperatures? What happens? So temperature is equal to 2/3 U, so it's going to be 2 over F, U over nk, right? And so at low temperatures, you're going to have very low energy, and it's going to tend towards zero energy, in fact. Anyway, you have to think about that yourself. And then finally, problem 3.7, calculate the temperature of a black hole and look at how the entropy behaves according to entropy, and we get some interesting results. And the caution is to stay away from black holes. They are not your friend. Okay, last thing I want to note here is I have a Patreon. I've been having people supporting me on Patreon off and on, $1 here, $5 here, and it's very much appreciated. I've tried to write personal notes to each of them. But a couple days ago, a guy named Tony Lee, he donated more than $20 a month, and so he is officially a supporter of this channel. And I wanted to thank Tony Lee for being the first to donate such a large sum of money. He has my eternal gratitude. You can support me via Patreon, or you can support me by buying textbooks through my Amazon affiliates link, which is in the description below. But to be honest, I think what I need now most for my channel is to get you to share this with your friends. YouTube is kind of weird in how it recommends videos and channels, and so a lot of good creators are just hidden because YouTube doesn't know that you want to see them. So please share my channel with your friends that might be interested in this content. Maybe they're taking a class with you. Maybe they want to review physics. Maybe they want to learn more about entropy or temperature. And guys, I hope you have a great day. Take care, and bye-bye.